check. Okay. Let's do this.
Can I just a really quick question?
No, you cannot. I'm sorry. It's not office hours. Okay, take your seats, please. Please take your seats. If you did not turn in your homework, do it at the end of class. If you did not pick up your homework from last week, do it at the end of class. I will have solutions to this homework assignment. Homework assignment 7. I will have those solutions posted this afternoon, and I will post homework 8 to be due next week. What else is on the horizon? Midterm 2 is our next class meeting. Okay. I have posted review problems and solutions to selected review problems. Hope you're all looking at those. What should you be studying? The review problems, the homeworks that we have covered since the last midterm. I believe we didn't have the master theorem at that time, so if you go to handouts, there's a special handout on master theorem problems. You guys, I'm lecturing right now, so you can talk if you like, but a few people want to hear, so if you want to talk, go outside, okay? Let me draw your attention to this master theorem problem sheet. It's a bunch of master theorem problems. If you do them all, you're going to be more than ready for whatever master theorem I throw at you. Bear in mind, though, that I didn't write this, and it has sort of a kind of a higher order case 2 in it than mine did. So some of these problems, our case 2 corresponds to their case 2 with the number k equal to 0. That's our case 2. So the nice thing about this is there are solutions, but some of them are case 2 with k equal to something other than 0. So you can ignore those. I won't ask you one like that. Review problems, master theorem problems, homework problems and their solutions. And then down at the bottom of the lower level of the study pyramid is examples I've done in class. Be able to reproduce any of those. Know the statements of major theorems. If I didn't cover the proof and it doesn't appear in a handout, I don't think I'm going to ask you to be proving it. But proofs I do in class, those are liable to show up on the exam. So the parenthesis theorem, the white path theorem, which I talked about last time, you should at least know the statements of those theorems and be able to use them in some other proof. We'll see how to do that today. Okay, so now we are up to section 23.4, which is a section on topological sort. What does that even mean to start with? Am I on the right? Let's go back. Last thing I talked about was classification of edges. There was a homework problem where you had to rewrite DFS so that it would classify edges. You'll see how that's done. Yeah. You expect a classification of edges here on the midterm, something that involves classification of edges. All right. I know I'm forgetting something. Oh yeah, PA4 is extended one last day to Wednesday, March 1. That's today, 10 p.m., which means I'm going to close the door on it tomorrow. Is everybody prepared for that? Yes or no? Anybody say no? How many people are desperate? They need more time. I'm not seeing anybody. Okay, so I might not close it at 10 a.m. sharp, but it's liable to be closed. So have something turned in by 10 a.m. tomorrow. Okay, topological sort is section 23.4 in the book. First, let's review the notion. So this is all about directed graphs. I mean, everything in this section and the next refer to directed graphs and not undirected graphs. So let's review the notion of what we mean by a directed cycle. First of all, there are directed cycles of all lengths greater than or equal to 1. We can't have a self-loop in an undirected graph, but we can in a directed graph. If that's x, then that's the edge xx, which is an ordered pair. Also, we can have a directed cycle of length 2. We can't have parallel undirected edges. By parallel, I mean the same ends. We can't have parallel undirected edges in an undirected graph, but we can have parallel edges that go in different directions in a directed graph. So if that's x and that's y, the two edges are x to y and y to x. Those are different ordered pairs. Maybe I should have labeled the edge xx. It's the edge that is formally the ordered pair xx. Okay, here's a directed cycle of length 3. Here's a directed cycle of length 4. So you know, of course, what I mean by a directed cycle now. Those are perfectly fine in digraphs. So here's a definition. A digraph is acyclic if and only if it contains no directed cycles. Nothing is asserted about the underlying undirected graph or undirected multigraph. We don't care about that. So there are different animals, directed and undirected graphs, when it comes to things like cycles. We're always talking about directed cycles. So a directed acyclic graph is called a DAG. Right? A DAG is the way we'll abbreviate that. Directed acyclic graph. Okay, how do you tell if a digraph is a DAG, is acyclic? This is how. Here is a lemma. A digraph G is acyclic if and only if DFS yields no back edges. Okay, now let's just pause for a second. And think about how DFS runs. We have these conventions about how to run it. The main loop of DFS is always run with, oh, by the way, let me switch that to document camera. Do that. Is that better? We have these conventions about how to run it. Main loop of DFS is, by convention and until further notice, run in the order of increasing vertex labels. And then the for loop in visit is run always, actually, in the order of increasing vertex labels. But if you were to change those orders, exercise, do it, you end up getting different DFS forest, right? And you end up having different edges classified as tree, back, forward, and cross. So it almost seems as if those classifications, tree, back, forward, and cross, are classifications of a labeled graph, right? But if you strip away the labels, then there is no longer any intrinsic classification of the edges as tree, back, forward, and cross. They depend on not just running DFS, but how DFS was actually run. Nevertheless, this is true. No matter how you ran DFS, with what convention on the orders of those loops, this is true. G is acyclic if and only if DFS yields no back edges. So all this stuff that we've learned about DFS, it seems like it applies only to labeled graphs, and it looks like it changes when we change the labeling or reorder the vertices. It actually is discovering some intrinsic structural information about the graph. In particular, it can be used to detect the existence of directed cycles. Oh, by the way, there's a homework problem where you're supposed to write and that you just turned in, where you're supposed to modify DFS in such a way that it will determine all of the connected components in an undirected graph, and then allow you to test, afterwards, whether two vertices belong to the same connected component in this undirected graph or not. How many people think they got that problem right? Okay, less than half, but a healthy number. You'll see the solution. So that's another thing that DFS is good for. Okay, remember, we've been on this sort of hunt for what is DFS good for since we started talking about it. Okay, in undirected graphs, you can find you can very efficiently figure out how many connected components there are and very efficiently tell if two vertices are in the same connected component. So that's one thing you can do about the structure of undirected graphs. Here's something that you can do about the structure of directed graphs. You can figure out if it's a DAG or not. Here's a corollary. Corollary means it's related. It's actually the contrapositive statement. Contrapositive. So it's logically equivalent to the lemma. Do you know what I mean by the contrapositive statement? Does everybody know what that means from CE 16? If you have a theorem of the form P implies Q, the contrapositive is not Q implies not P. And they are logically equivalent. So they're either both true or both false. I'm going to actually prove this contrapositive, the corollary, and it says that a digraph contains a back edge if and only if DFS yields no back edges. Huh? It yields a back edge, sorry. Produces, sorry, a back edge. Thanks. Now does it make sense? Huh? Digraph can, oh, hang on a second. This is one of those cases where I want to throw the piece of paper away. I'm going to do that. This bugs me because it wastes time. A digraph is acyclic if and only if DFS yields no back edges. That's right. And here's the corollary. It's the contrapositive. Actually, it's not the contrapositive because this is if and only if. It's just the negation of the left and the negation of the right. I won't even call it contrapositive. So it's logically equivalent. An equivalent statement. A digraph contains a directed edge. A directed cycle. That's the negation of being acyclic. If and only if DFS yields a back edge. I state it in this kind of complementary way because that's the way I want to prove it. So obviously these two statements are logically equivalent. Let's prove the corollary and thereby proving the lemma. It's an if and only if statement. So I have a left to right and right to left. Let's first do right to left. In other words, suppose DFS produces a back edge. This is the easy direction. Well, then obviously there's a directed cycle. What's the directed cycle? Start at the, what's a back edge? It goes from a descendant to an ancestor in some DFS tree, right? So what do? Start at the ancestor, work your way all the way down to the descendant along tree edges, and then go back up to the ancestor using the back edge. So it's all tree edges and one back edge. That's your directed cycle. Then obviously, that's a dangerous word to use in a proof. It's sort of like, if it's so obvious, it should be easy to prove, okay? Obviously, there is a directed cycle. So start at the ancestor, go down tree edges until you get to the descendant. And then travel up from the descendant to the ancestor along your back edge. And this is your directed cycle. Okay? Remember, the directions of the edges are always going to go down. Okay, that's the easy direction. I consider that too easy for the exam. But you should know it anyway. Okay. So here's the other direction. This is harder. It's not hard. It's a little harder. It's a little more involved. It uses the white path theorem. Some of you have probably read this. I'm sure this is one of the problems I gave you on the review sheet, right? And I'm really just reciting. And probably the problem I gave you on the review sheet is this direction. That is, suppose the digraph contains a directed cycle. Show that DFS must produce a back edge. Assume G contains a directed cycle. Must show DFS on G produces a back edge. Okay. So we have to show that the existence of a back edge. And we're going to use the white path theorem, which I stated last time. I did not prove it in the interest of time. I used to prove it years ago. Somehow I had more time in this class, and I would prove the parenthesis theorem, and I would prove the white path theorem. I did all kinds of things. If you took this class 10 years ago, you got 1.5 times the same amount of material that I'm covering. I don't know how that's happening. Well, besides the fact that we're losing 5 minutes of class, that I know. I don't know why everything goes so much slower. All right. Do I sound like I'm complaining about life? I am. Okay. G contains a directed cycle. All right. So, call the directed cycle C. So let's draw a picture of it. You know, pictures don't prove things, but it's okay to have a picture in your proof. So we have some directed edges, and I won't try to draw the same thing, the whole thing, because I don't want to make any assumption as to how long this cycle is. But there is some way to go all the way around. Here's the directed cycle. It is C. Okay. That's all I know. And we're going to run DFS on this. And the argument I give can have really make no assumption about the ordering of the vertices, the labeling of the vertices, or even the order in which we run any of those loops. So, let X be sorry, let me make sure I get this right. Let Y be the first vertex on C to be discovered. By DFS. So let's say it's right there. Okay. So think of the movie, right? The whole graph is one frame in the movie, and the distribution of colors is one frame. And Right, each frame is a different timestamp. A discovery event, that is a graying, or a finishing event, that's a blackening of one vertex. So each frame changes one color of one vertex. All right. So there's this cycle, and there is, in this movie, one vertex on that cycle which is discovered first. Give it a name. Y. Okay, let's also give a name to the vertex that precedes Y along that cycle. Let X be the vertex that precedes Y along C. You see what I'm saying? What comes right before it as traveling around, as you're traveling around. Okay, I claim that XY is our back edge. Why is that? Well, since Y is the first vertex to be discovered, when Y is discovered, all vertices are white. And since there's a cycle, the white path theorem guarantees that every vertex here, since there's a white path from Y to each of them, has to become a descendant of X. I'm sorry, a descendant of Y. So, since at time of discovery of Y, all vertices along C are white. That's because it's the first one to be discovered. There exists a white path from Y to X, namely travel along the bottom edge of the cycle. They travel along the rest of the edges of the cycle. Okay, so at the time of discovery of Y, there exists a white path from Y to X. That's exactly the hypothesis of the white path theorem. By the white path theorem, X is a descendant of Y in some X becomes, by the time DFS is over, a descendant of Y in some DFS tree. So therefore, the edge from X to Y is a back edge, because it goes from descendant to ancestor. End of proof. That's what I needed to prove, that there exists a back edge. Okay, so that's the other direction. It's a little bit longer, requires a little bit more writing and a little bit more, understanding of what's going on. Requires that you remember the white path theorem and what it says, exactly what it says. I have put this on many midterm 2s, and when I don't put it on midterm 2, I almost always put it on the final exam. So my suggestion is, be prepared to reproduce this proof at our next class meeting. And don't think, I stare at the picture and say, yeah, I understand that, and then and then walk away. I mean, the picture is not the proof, right? You need to say everything that is being said here. In particular, it needs to be clear from your proof when you write it that you know what the white path theorem says. Often, I sometimes just ask, state the white path theorem, and then prove this direction only, right? Well, I'm going to drop it at that. But now this tells us, this proves conclusively that DFS is good for something in digraphs too. Now, what's a topological sort? Let G be a directed acyclic graph. A topological sort of what? What are we sorting? A set. What set? The vertex set of G. A topological sort of vertex set of G is a linear ordering of the vertices wait a second, how come there's a space there? Linear ordering of the vertex set such that if xy is a directed edge in G, then x comes before y in the ordering. So does everybody know what I mean by a linear ordering? It's just arrange the vertices on a horizontal line from left to right. The one on the left is the earliest, the one on the right is the latest. It's a ranking, if you will, of all the vertices in some numerical order, right? First, second, third, fourth. That's what I mean by a linear ordering of this finite set of vertices. So, in other words, you ought to be able to redraw the graph in such a way that all the vertices are on a horizontal line and all the edges travel from left to right. That's a topological sort. And notice I say a topological sort. There might be more than one. Sometimes there is only one, but there might be more than one. Notice, first of all, that you can't do this in a directed graph that contains directed cycles, can you? Because if there's a directed cycle, how are you going to have all the edges go one way? There's got to be, you've got to get back to where you started from if you got a cycle. So this cannot happen if the digraph has a connected cycle. This could only happen in a DAG. In fact, every DAG admits such an ordering. I won't prove that, but I think it's fairly obvious. For example, here is a DAG. You verify that it is a DAG. That is, that there's no directed cycles. There's the underlying undirected graph. Here are the directions. Let's label the vertices. I don't know why I labeled them in that order. Okay, notice there are no directed cycles, right? Look, try as you might, you can't find one. If I just reversed one or two edges, I could get directed cycles, but it depends entirely on the directions. So here's the topological sort. So take the vertices and put them in the order 1, 4, 2, 3. And now draw in all the edges. I've got a directed edge from 1 to 4. What do I got? 5 edges now. Let's make sure we don't miss one. 4 to 2 and 2 to 3. Okay, that's the Z here. Zoom, 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 right? Then 1 to 2 and 4 to 3. All edges travel from left to right. So that confirms that the ordering of the vertex set 1, 4, 2, 3 is a topological sort. Are there any more topological sorts? No, actually there isn't. There aren't any other topological sorts in this example. Okay, so what does this have to do with DFS? DFS will not only figure out if a digraph is a DAG, but it will calculate a topological sort in that DAG. You know, we don't spend too much time on applied graph theory here, but you can sort of think about how good such a thing would be to have. Suppose you had a set of tasks to be performed in some order. But you don't have an ordering. But you do have a bunch of relations between subtasks, a list of tasks. Right? And you know that one task has to be performed before 3 or 4 other tasks. Otherwise, they can't be done. So there's some kind of ordering of tasks, but it's not an ordering that imposes one specific sort on you. So say the tasks are the vertices and the order relations are the directed edges. Then you want a schedule. You know, what do I do on day 1? What do I do on day 2? And suppose it's a really complicated task, like building a skyscraper or building the space shuttle. Many, many tiny little big tasks and little tasks. Some have to be performed before others. How do you create a schedule in order to accomplish the whole project? Well, first of all, you hope there are no cycles of dependencies. If you run DFS on the resulting digraph and you find a cycle, you find that the way you split the problem up into subtasks doesn't work. That'd be nice to know before you start. And also, if there are no cycles, you'd like to have some kind of a schedule. Do this on day 1, this on day 2, this on day 3, this on day 4. Then all the dependencies, that is, one thing before the other, are going to be satisfied. Okay. So here's a theorem. I won't prove it. It's stated and proved in the book. To perform a topological sort, I'll just say top sort, on a DAG G, run DFS. This is sort of a meta theorem here. I'll just bullet it. I won't even number a meta algorithm, all right? Run DFS G as vertices finish, push them onto a stack. When DFS is done, the stack is your topological sort. Top to bottom. That's the theorem. So run DFS as every time a vertex finishes, so we're doing a return from visit, push that vertex onto a stack, a separate data structure that you keep. By the time you're done, the stack contains from top to bottom the vertices ordered by decreasing finish times. So equivalently, we could just run DFS on G, then sort by decreasing finish times. Okay, interesting. And if you run DFS enough on enough digraphs, you'll sort of, you'll come to believe this theorem. I recommend that you read the proof in the book yourself. I'm not going to cover the proof here. You know, all these proofs that I'm skipping, they would be great for us to study. Say that again? Well, DFS is already a recursive algorithm because it contains this recursive part, visit. I guess what you should have asked is, can DFS be run iteratively? Can you run it in a loop? And the answer is yes. You know, there's a general principle in algorithm design that any iterative algorithm can be translated to a recursive algorithm, and every recursive algorithm can be translated to an iterative algorithm. It's not necessarily good to do that. I mean, there's some algorithms that want to be recursive and some algorithms that want to be iterative. It's easy to do certain things a certain way. What happened to my bottle of water? Huh? Did anybody see it? It's over there. Get over there. No wonder I'm parched. Okay. Hang on just a second. This is why I'm running out of time. I'm wasting so much time. Okay. I do expect you to be able to do this on an example. So let's look that over. So here's a slightly larger example than the last one. I'll tell you what, let's do it the quick way. Okay, what are the labels? Don't ask me why I labeled it exactly this way, because it works. It does what I want it to do if I label it this way. Okay, so let's just run DFS without drawing the adjacency list representation. Let's just eyeball it and go by our conventions. The first thing you can discover, any vertex could be started at. Remember, there's no source in DFS, but always prefer the lower label first. So the first thing I do is I discover 1. It's a root. Here, let's put it here. there's 1. And then what can I discover next? Well, the lowest I can discover 2, 3, or 4. I prefer 2 because it says a lower label. And then, so here's 2. Return from 2 to 1 because I can't discover anymore. So I can discover 3 or 4. I prefer 3. Drawing the DFS forest right now. So from 3, what can I discover? I can discover 4. And I prefer that. From 4, what can I discover? 5. From 5, what can I discover? Nothing. So go back to 4. What else can I discover from 4? 6. What else can I discover from 6? Nothing, because 5 has already been discovered. So I back up. So I back up from 6 to 4. Nothing new to discover from 4, so I back up to 3. By this time, 5's been discovered, so I back up to 1. By this time, 4 has been discovered, so I'm done. Okay, so there's DFS. And this picture now tells us the parent structure, the discover and finish times. Discover, discover, finish, return. Discover, 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 finish, return. Discover, finish, 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 finish. So I can get all the finish times and discover times too, just by kind of rerunning it over this, this tree. DFS forest happens to have 1 tree in it. Okay, so what does the stack look like? The stack goes in decreasing finish times. So every time I finish, I should push onto a stack. Discover, discover, finish, then return, then discover, 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 finish the 5, then return, then discover the 6, then finish the 6, return, finish the 4, return, finish the 3, return, finish the 1. So here's the stack. And the stack, top to bottom, is a topological sort. You could also classify tree back forward cross if you wanted to. You'll notice that there is no back edge, is there? Yeah, I didn't stop to check that this was a DAG, did I? Notice that there are no directed cycles, there better not be, and there is no back edge. Try as you might, classify the edges, you won't find a back edge. So this is a DAG. So let's arrange the vertices. Let's check that it is a topological sort. Arrange them in the order 1, did I get this right? 1, 3, 4, 6, 5, 2. Yes. 1, 3, 4, 6, 5, 2. Okay, so I have 1 to 3, yes. 1 to 4, left to right. 1 to 2, that's also left to right. Then 3 to what? 3 to 4, and 3 to 2. Oh, also 3 to 5. Right? 3 to 4, 3 to 5, and 3 to 2. Let's go around the bottom. Then 4 to what? 4 to 5 and 4 to 6. And then what? 6 to 5. And then, let's see, 6 to 5. And then 5 goes nowhere. Notice, I think I've got all the edges, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, all 9 edges. I didn't leave any out. So that confirms that this stack gave us a topological sort. Okay? Probably going to ask you to do something like this on the midterm. So I suggest and give you as an exercise, draw some digraphs and do this. Maybe bigger than the one I just gave you. Just make sure you can do it. Do it enough times so that it doesn't seem strange. You know, the second midterm is usually, not always, but by most students considered a little easier because it's more computational. Again, I'll give you the algorithms, but if you need to look at them, you don't know them well enough. Do a lot of this. Okay. Here's an exercise. Pertaining to this example. This DAG has, well, I don't see them, but this DAG has 3 more topological sorts. Topological. G-I-C-A-L, sorts. Forget it. Just, I'll fix that word later. Find them. My spelling module is not working too good. I'm talking as if there's like a sub-program in my brain that spells things, and it doesn't always work. Okay, so can you see what they are, though? I mean, think about, here's how you find them. Just stare at this one topological sort and pretend the edges are made out of rubber bands, so you can kind of move them around. So if I move this 2, if I move this 2 between the 6 and the 5 and stretch this 5 out and put the 2 in its place and had the 6 to 5 go over the 2, it would still be a topological sort if I just swapped the 5 and the 2, basically. And if I put the 2 between the 4 and the 6 and left everything else the same, that would also be a topological sort, right? And if I put the 2 between the 3 and the 4, that would also be a topological sort, right, for the same reason. But once I can't get the 2 behind the 3 or the 1, right? So that's the only place I can't put the 2. And there's no edge from any of these to 2, so that's why I'm free to move the 2 around. Okay, I don't know of a way, there probably is a way, but I don't know of a way to count the number of topological sorts in a digraph, in a DAG. It's an interesting problem. Yes? Because how did I come up with this order? This is the stack. The theorem says the stack is a topological sort. It doesn't say it's the only one. There may be others. What I just said was I don't know of a way to, other than eyeballing it, I don't know of an algorithm that will count the number of topological sorts. That's an interesting question. You might think about that. Here is another exercise. Here's a remark. No, here's an exercise. You can use this topological sort algorithm that is DFS together with pushing onto a stack. Now I can spell it. To sort an array. Okay, so the exercise is figure out how. Okay, that's a nice, you fiddle around with it for a while, you'll be able to figure that out. Okay, so that is 23.4, correct? Now, did I have a problem on the review sheet? I think I did. Jeez, I hate that. If I go to the review sheet for a second, did I have a problem regarding BFS? They give you specific orders for the main loop of DFS in problem 2. So 2C. We haven't done that yet. Find the strong components. So we might not, I'm going to start talking about that right now, and that is, I think that's the only thing that we haven't covered. So this is 23.5. Section on strongly connected components. And I'll abbreviate that SCC. SCC, it means strongly connected component. Okay, does everybody remember the definition of a strongly connected component in a digraph? Who still remembers it? Who could write it down if I asked you to write the definition on a midterm, on a pop quiz right now? Okay, so one person raised their, 2, 3, 4 people raised their hand. Maybe I should review that. So recall, a subset S of the vertex set of a digraph G is called strongly connected if and only if for all x, y in S, x is reachable from y, and y is reachable from x. Okay, so notice that every singleton subset of the vertex set is strongly connected, right? Because if your subset of the vertex set consists of just one vertex, then within that small set, you can get from anywhere to anywhere. How? What path? The trivial path, right? Don't forget the trivial path. So, more generally, or definition, S subset of vertex set in G is called a strongly connected component if and only if two things hold. One, S is strongly connected. And two, what's the part two? Can somebody tell me? Yes? S is maximal with respect to property 1. WRT means with respect to 1. In other words, what does maximal mean? It means it can't get bigger. It can't get bigger and stay strongly connected. So remember, I'm talking about subsets of the vertex set. The more vertices you throw into a subset, the harder it is to be strongly connected. The more constraints you're putting on the connections between those vertices in order for it to be strongly connected. You see why that is? So we should be concerned with maximality. When can you not get any bigger? The more vertices you put in, the more places you've got to get to and get back from, wherever you start. So the bigger it is, the bigger a subset of the vertex set is, the harder it is for it to be strongly connected. And so what's the point where you can't get any bigger? Those are the maximally strongly connected subsets of the vertex set, and those are the strongly connected components. Question? Later, please. Louder. With respect to. WRT is with respect to. Okay, so DFS can be used to find the strongly connected components in a digraph. By the way, notice that we don't care if the digraph is a DAG or not, right? A DAG, like this one, notice that the strong components are the strong components are the singletons. Because in a DAG, once you leave a vertex, you can't get back to it because there are no directed cycles. Right? So if there are two vertices in a subset, you might be able to get from one to the other, but you certainly won't be able to go back the other direction because there are no directed cycles. So therefore, the strongly connected components are, I was supposed to blacken all of these, so I'll do that. But in general, in a digraph, there might be more than one set, more than one vertex in a strong component. Okay, so let's at least state how to do this before, and then I don't think I'll have time for an example, but I'll at least state it. We can use DFS to find the strongly connected components of a digraph. How? Again, it's a sort of a meta algorithm. I'll just give a bulleted list of things. Call DFS. So run DFS on G. As vertices finish, push them onto a stack. Then compute the transpose G transpose of G. What is the transpose of a digraph? What do you suppose that means? Swap every vertex. Didn't quite make sense. Go ahead. Swap every direction. Right, that's what you meant, right? I knew that's what you meant. So out in the middle of the night, take all the one-way street signs and reverse them. Okay? Think of it as like an act of vandalism or something. Okay, so reverse all the one-way street signs. Reverse all directions. So that's a different digraph. Right? That's a new and different digraph, but it's related to the other because it's the transpose. Why is it called the transpose? Look at the adjacency matrix. It's actually the transposed matrix. Transpose the adjacency matrix. That's the adjacency matrix of the transposed graph. And then run DFS on G transpose. But this time, order the main loop of DFS, not by our convention of increasing vertex label, but by decreasing finish times from the first call. In other words, we run the loop by just popping off the stack. Now, do that. Here's a theorem. Stated and proved in the book. I won't prove it. We're just going to do it. When this is done, the strongly connected components of G are the vertices in each of the trees of the DFS forest obtained from the second call. In other words, each tree in this after you run the second call, you get a bunch of trees in the forest. The vertices in each tree form, those groups of vertices form the strongly connected components of G. By the way, notice that the strongly connected components of G and G transpose are one and the same. Are the trees in the DFS forest from second call. Okay, so I guess the main question is this going to be on the midterm? Since I don't have time to run an example, I'll say no. We'll go as far as topological sort. We won't go as far as this. However, this is exactly what you're going to do on PA5. You're going to implement all of this in PA5. All right. If you did not turn in your homework, please put those papers up here. If you did not pick up your homework, please come down at the foot of the stage and get these papers out of here. Sorry for going over. Yes?
I have a question about DFS.
Yes?
I was looking through the pseudocode, and I was wondering, could you do the same thing if you just apply the colors white and black?
You could get rid of the colors altogether if you really want.